How to calculate non-standard cell potential using the Nernst equation. Going to be the topic of this lesson. My name is Chad. Welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. I'll leave a link in the description for where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post one, subscribe to the channel, click the bell notification. All right, so calculating non-standard cell potential. And in the last lesson, we learned how to calculate standard cell potentials. And this should be a little bit reminiscent of something we learned in thermodynamics. In thermodynamics, we spent a lesson learning how to calculate the standard value for delta G using some thermodynamic data in the back of your textbook. And then in the next lesson, we learned how to calculate the non-standard delta G. And we had a similar looking equation to this one. So this one says that your non-standard cell potential is equal to the standard value minus this fudge factor that involves the reaction quotient. And you might recall that we had, back in the last chapter, a similar type equation for delta G. Delta G equals delta G standard plus RT ln Q. And in fact, this Nernst equation actually comes from this equation, truth be told. So it turns out we're going to learn in the next lesson, but I'll allude to it here, that delta G equals negative NF E, where E here is the E cell, and maybe I'll just put that with the epsilon to kind of match things up here. And you could do it both under standard or non-standard conditions. Under non-standard conditions, it's delta G that's related to E, both under non-standard conditions, or delta G standard is related to E standard. So if we substitute both of these in for delta G and delta G standard right in this equation, that's kind of where the Nernst equation comes from. So notice if we took negative NFE, so that's in place of delta G, and then instead of delta G standard, we'll substitute in negative NFE standard. Cool. You'd factor out the negative NF, and then you'd find out you'd end up dividing that NF through over here, which is where you get this negative RT over NF ln Q term. So that's where that comes from. So I'm not going to go through the entire derivation here, just wanted you to kind of see where it's coming from. But that's the Nernst equation. The whole point is to calculate non-standard cell potentials. Now, one thing you should note is commonly, R here is the universal gas constant, 8.314 joules per mole Kelvin. So F here is Faraday's constant, often rounded to 96,500 coulombs per mole of electron, or more specifically 96,485 coulombs per mole of electrons, but usually rounded to 96,500. Going to give you a pretty close answer either way. And then finally, most commonly, they talk about this at 298 Kelvin. Well, if R and F are constants, and if you're only ever talking about 298 Kelvin, then T becomes a constant. An N here, it turns out, is the number of moles of electrons transferred in the process or showing up in a balanced half reaction or reaction, depending on the case. But if, and that's variable depending on the reaction, but the other three here, there would be constants as long as we're talking about 298 Kelvin. And a constant times a constant divided by a constant is going to be another constant. And it turns out if you take 8.314 joules per mole Kelvin times 298 Kelvin divided by 96,500 coulombs per mole of electrons, you get 0.0257. And you can summarize it as a constant. And so oftentimes the Nernst equation is reported this way. And again, it only actually is applicable as long as you're talking about 298 Kelvin. But sometimes professors just say, you know what, this is a pain in the butt. I'm only ever going to ask students about 298 Kelvin, and I'm going to give them this equation instead. Well, it turns out even earlier in time, before calculators were prominent, so it's been a minute, that natural logs are a pain in the butt. And so oftentimes, instead of using natural logs, they used log-based tens, because a lot of those calculations you can do in your head, or you could use a slide rule, or there were tables of them published and stuff. And so oftentimes they would turn natural logs into log-based 10. And you simply have to multiply it by an extra factor of like 2.303. And so if you multiply this guy by 2.303, you get 0.0592, and then you can use the log base 10. And even though it's, been quite a while since we didn't have access to good calculators and stuff, you'll find this version of the Nernst equation often still reported as well. Now, whether you've got the original actual Nernst equation, or whether you've got one of these two simplified versions at 298 Kelvin, either with the natural log or the log base 10, you've got to be prepared to use it, but it's all used for the same thing, to calculate non-standard cell potential. So let's take a look at an example. All right, so the question we're going to take a look at is we're going to calculate the cell potential for this lovely reaction under these conditions at 298 Kelvin. And so in this case, we can see that we're definitely not under standard conditions because these are not equal to 1 molar. Again, standard conditions means aqueous species are all 1 molar concentration, gaseous species all 1 atmosphere partial pressure. So definitely not standard conditions. And the moment you're asked to calculate cell potential under non-standard conditions, that's what the Nernst equation is for. And again, it could be presented to you in any one of these 3 forms. Use whichever one is being provided for you. So I'm going to use the original here. So, and we're told to find this at 298 Kelvin, and that's how you'd also know that either one of these would be applicable as well, and will lead you to exactly the same answer if you do the calculation correctly. So, but in this case, to be able to calculate your non-standard cell potential, you first have to actually calculate the standard cell potential. And sometimes it'll just be given for you, but sometimes they're going to provide you with the appropriate reduction potential so you can figure it out. And technically, we actually figured out the standard cell potential of this exact reaction in the last one. So, and in this case, your standard cell potential. So we can see that zinc 2 plus to zinc is reduction, and that's negative 0.76 volts as a reduction. But cobalt to cobalt 2 plus, that is the reverse reaction. And whether I change the sign and then add it to negative 0.76, or whether I do cathode minus anode, where the minusing changes the sign for me, either way, it's going to be negative 0.76 plus 0.28 volts. And so your E standard here is going to be negative 0.48 volts. And so now that we've got E standard, now we can do the rest of the calculation adding in this fudge factor. So, and R again is 8.314 joules per mole Kelvin. Temperature is given as 298 Kelvin. So, and then NF here, and if you look here, N is the number of moles of electrons transferred in the reaction, and it's the same N as what you're balancing an overall reaction to. And so it turns out you can apply this equation to a half reaction or the entire reaction. Well, if it's for a half reaction, like one of these or something, you just see, oh, if it's just for this half of the reaction, well, then it's 2 electrons, and you can see it. But if it's for the entire balanced reaction, you're going to have to figure it out. And so in this case, in going from 1 zinc 2 plus to 1 zinc, that's a 2 electron process, 2 electrons being gained, a 2 electron reduction. And from cobalt to cobalt 2 plus, that's 2 electrons being lost, a 2 electron oxidation. And so 2 electrons lost, 2 electrons gained, this is 2 electrons being transferred, and that's N. So notice the number of electrons lost and gained should be the exact same number if it's been properly balanced. All right, so our N here is 2, and we'll write that as 2 moles of electrons. And then finally, Faraday's constant F, which is often rounded to 96,500 coulombs per mole of electrons. So, but if they give you a more specific number, like 96,485 coulombs per mole of electrons, well, all means use whatever they give you. And then finally, we're going to have the ln of Q. Now, Q here is just, products over reactants raised to the power of their coefficients for whatever conditions you happen to be under. It doesn't have to be at equilibrium. And so in this case, let's solve Q first and just plug it in. But Q is going to equal the concentration of cobalt 2 plus all over the concentration of zinc 2 plus. And a reminder that solids do not show up in reaction quotients or equilibrium constants. And so in this case, the cobalt 2 plus concentration is given as 0.10 molar, and the zinc concentration is 0.0010 molar. So, and dividing by 0.001 is the same thing as multiplying by 1,000, which just moves that decimal over 3 places, and this is going to get us 100. So Q is 100, and so natural log of Q, natural log of 100. And now we're ready to do some plug-in and chug-in with our calculator. Now again, truth be told, so 8.314 times 298 divided by 96,500 is simply 0.0257, and then we'll have to divide by n, the 2, and then take the natural log of Q, which in our case is 100. So that's how you might have used this one. So, and had you used this version instead, the big key is that you'd have to use the log base 10 instead of the natural log. But again, whichever form the Nernst equation is provided for you, that'd be the one I recommend you use here. So in this case, we're going to have negative 0.48. So minus 8.314 times 298 divided by 2, and I'll put all the denominator here in parentheses, so divided by parentheses 2 times 96,500, and parentheses times the natural log of 100, and we're going to get negative 0.54 volts. Oh, I lost my negative sign. Okay, and so we can see that this reaction got a little more negative on its E cell than the standard value. Standard value is negative 0.48 volts, and our non-standard value here is negative 0.54 volts. It's not spontaneous under standard conditions. It's definitely not spontaneous under these conditions either, but it's even more non-spontaneous or even less spontaneous, or however you want to look at that. So being a more negative E cell here, and we could have predicted this. So in addition to be able to do calculations with the Nernst equation for these non-standard cell potentials, you also kind of want to get a qualitative look, a big take-home here. So when a reaction reaches equilibrium, that's when your E cell is going to reach 0. So let's just say this reaction had reached equilibrium. So if we measured E cell, it would be 0. Now let's just say, though, that we added a bunch of zinc 2+ at that exact instant. It reached equilibrium, and then we added a bunch of zinc 2+. Well, it's not going to be at equilibrium anymore. Le Chatelier would call this a stress placed on the system at equilibrium, and it's going to shift to the right to counteract the stress. So adding zinc 2+, increasing its concentration, causes a shift to the right. Well, if it's shifting to the right, that means it's no longer at equilibrium. If it's no longer at equilibrium, then E cell is no longer going to be 0. And what a shift right ultimately means is that the forward reaction is now spontaneous. And if the forward reaction is spontaneous, then E cell's got to be a positive number now. And so the take home here is that anything that causes a shift to the right causes your E cell to go up, get more positive or get less negative, same diff. So we might just sum that up by saying anything that causes a shift to the right increases the cell potential, the voltage. And therefore, anything that causes a shift to the left, making the reverse reaction spontaneous, the forward reaction non-spontaneous, that's going to cause E cell to go down, either less positive or more negative. And that's a big take home. And so notice looking back at this here with the zinc 2+ and the cobalt 2+, we could have looked at this and said, oh, the zinc 2+ concentration is lower than standard conditions. And lowering a reactant leads to a shift to the left. And then we look on the other side and say, well, the cobalt 2+ though is also less than standard conditions, less than 1 molar, and that would cause a shift to the right. And in this case, though, the question is which one is further away from standard conditions. They both have the same coefficient of 1 in front, so there's no difference there. Just a reminder that coefficients show up as exponents. But in this case, this one's so much lower that the shift left being caused by the zinc 2+ being lower is more significant than the shift right by cobalt 2+ being lower than standard conditions. And so overall, we probably should have accepted overall this is shifted to the left relative to standard conditions, which means that E cell should be even more negative or less positive than the standard value of negative 0.48 volts. So something we might have qualitatively expected for this answer to come out even more negative than the standard value. Cool, that is your Nernst equation. So there are some, places where you can definitely make a mistake in the calculation. So however, if you're given one of these simplified versions, I highly recommend you go there. And again, they only apply to 298 Kelvin, but oftentimes that's the only temperature many a professor will even ask you about. Now, if you found this lesson helpful, like and a comment letting me know are pretty much the best things you can do to support the channel. And if you're looking for general chemistry practice or any preparation for your final exams, including practice final exams, then check out my general chemistry master course. I'll leave a link in the description. A free trial is available. Happy studying.